Let's look at a very interesting result about the Riemann integral. Let's suppose that f has a Riemann integral on a symmetric interval. That is, we fix a positive a and we write an interval, the additive inverse of a, to a. That is, this particular interval is symmetric about the origin. So for instance, we could say negative pi to pi or negative 1 to 1. Now, the result is this. If f is an odd function, then this integral is identically 0. That is, if we integrate f on the symmetric interval, we get 0. If f is even, then the integral of f on the symmetric interval is twice the integral of f on the interval from 0 to a. So in both cases, we have a huge simplification. In the odd case, we just get 0, no work involved. In the even case, we replace the lower limit here with a 0 and then double the result. So again, another simplification. Why is this true? Well, let's just consider the integral on the symmetric interval and use additivity. So we can just, again, we can take 0. 0 is our favorite real number for using the additivity theorem, but we could use any one we want. But since we're lazy, we'll choose 0. So we'll write this integral on the symmetric interval as the integral of negative a to a of f plus the integral from 0 to a of f. And I wrote this integral first just to make the flow look a little better. Now, for this second integral, what we're going to do is interchange the limits of integration. And when we do that, we introduce the negative sign. Now, this one is fine. We don't want to do any more to this, but we want to operate some on this. So for the second integral, what we're going to do is replace x with its additive inverse. So replace x with negative x. Now in doing that, we're going to see that that automatically changes the limits of integration. That is, the additive inverse of 0 is 0, and the additive inverse of a is a. So that's the easiest change. The negative we have built in. And then, of course, here we replace x with negative x, and we replace x with negative x in the differential. Now, of course, the differential of negative x is just negative 1 dx, which we have here. And, of course, f of negative x is fixed. But this is a constant which can now be factored. Negative times the negative will give us the positive. So we've rewritten the second integral as this integral. So now, as I've written here, we have the recipe. That is, f on the symmetric interval is now expressible as the function integrated from 0 to a plus f of the additive inverse of x integrated from 0 to a. So I call that the recipe because that's really all we need to do to finish the proof. So now, when f is odd, all we have to do is just go over to this red box. When f is odd, the negative factors. So the negative comes out. And then, of course, this is just multiplication by negative 1, which can be factored using the properties of the definite integral. And then, of course, these two real numbers are just additive inverses. We get 0. Now when f is even, let's go up to the box. F of the additive inverse of x is just f of x. That is, the negative absorbs. So now we just get 2 copies of the integral from 0 to a, which gives us 2 times the integral from 0 to a of f of x. So what we see here is the actual principle is relatively easy to prove, but the result you'll never forget. Now, you can often think about this in terms of graphs because you know odd functions have origin symmetry and even functions have y-axis symmetry, so you can draw pictures and convince yourself that this is valid. But we do need to use the properties of the definite integral to give a rigorous proof. And we are done.